minor bar. Okay. Now questions were obtained. Please note that if your friends are not attending, they are not giving the quiz, please tell them that it is easy to pass in my course. Very easy. You have to really work hard to get a fail grade. Okay. But if you get a fail grade because of not attending, because of not writing the quiz, I usually don't take self-study. Don't apply for the self-study. I have not given self-study in last 12 years and I will not give. So note down that you will not get a self-study. Even if it is extending your semester, you will not get a self-study in this course. So you better do it in a regular channel, and in a regular channel it is easy to pass. Okay. And if you miss and then write a very good nice application to DUGC, I will make sure that it will not go through. Okay. So please attend it in a regular channel and I am damn sure you will get a pass grade. You will have to work hard to get a fail grade. Students get fail grade in my course only when they themselves want to get a fail grade. Otherwise they don't get. So it is difficult to get A grade and fail grade. These are the two grades which you will have to work really hard to get. Otherwise you will get it easily. Okay. So please do the course honorably. Don't try to do a course by back channel. I don't allow that. Okay. Alright. So in the last class, again one more request. Please do not bunk the major examination. Write the major examination in a regular channel. Major examination and all the quizzes and minor are open book. But if you compel me to write a re-major for you, then it's a closed book and complete syllabus. Okay, it is closed book and complete syllabus. So unless it is really difficult to attend, only in those circumstances you miss. Otherwise, don't miss just for sake of missing, because you know how people do that. I know very well. Okay, so please don't do that. Alright. So in the last class we started looking at the higher order systems. We said higher order systems we can get in three ways. Either we are having multiple capacities in series. So multi-capacity processes like distillation column, absorption column, that leads to a higher order system. Isn't it? That is one way of getting a higher order system. The second is system associated with date time. That gives you a higher order system. And the third option is when we are having an inverse response. When we are having an inverse response, typically we get a higher order. That is what we have seen in the last class. When we get an inverse response, again both the batches have done their tutorials. Inverse response we get whenever there are two processes competing with each other, isn't it? And you can see that whenever we have a positive zero, in that case we get an inverse response. So in a typical case like this, where there are two processes competing with each other, we can get an inverse response only when the second process is faster than the first one. And if you do the mathematics, you will find that you get an inverse response whenever you have a positive zero. Okay, that is what we have seen in the tutorial also. Again, inverse response physically, how we get the inverse response physically. So this is the system we have studied in the last class. This is a drum boiler. What we are saying here is, in this drum boiler, let's say F1 is the flow rate of inlet water which is coming inside the drum boiler, isn't it? Typically, the temperature of the fresh water is going to be lower than the temperature of the liquid which is present inside the boiler, isn't it? So what will happen? Because of this inlet of fresh water inside the boiler, the average temperature inside the boiler is going to decrease, and because of that, whatever the bubbles those are entrained inside the liquid, they will contract, and because of that, you will see that the liquid level is going to drop. Okay, so that is one observation. So typically the liquid level is going to drop. So this is nothing but a first order process in a negative direction. And the second case is because of inlet of water, what will happen? Inlet of water, since the fixed amount of heat is supplied and fixed amount of water is vaporized inside the boiler, addition of the inlet feed water is going to increase the level of liquid inside the tank in a pure capacity way. Okay, so whenever output is constant, we likely to get a pure capacity process, isn't it? So how the height of the liquid is going to increase here, that will be governed by a pure capacity process. So you can see that we will get a pure capacity process in a positive direction and we will get a first order process in a negative direction. Both these are competing with each other, isn't it? In this particular case, we are going to get an inverse response only if the second process is faster than the first. Okay? Alright? This is what we have seen in the lab. Then towards the end we said, let's look at the feedback control system. Feedback control system. So feedback control system is what? Whenever there is a disturbance coming into the system, this disturbance is going to mess up the state of the system, isn't it? My objective is to apply the corrective action so that the impact of this disturbance on the system I can mitigate. That is what the feedback system is, isn't it? So in this case you can see that the disturbances are keep on coming to the process. Then there is a manipulated variable which is in your hand. You can change this manipulated variable depending on what you want, isn't it? And y is the output. So because of this change in disturbance variable, this y gets messed up. I wanted to change this m in such a way that even though this d is changed, ultimately my y remains fixed to a set point value, isn't it? This is what the logic behind the feedback system is. So typically what we do, this is the process, d is the disturbance, manipulated variable here. Both are coming in the system and y is the output. So typically what we do, output we are going to measure by using the measuring devices like thermocouple or differential pressure cell, etc. Isn't it? So we measure the output and then this measured output is denoted by ym. Note that this ym may not be same as y. This ym may not be same as y because this measuring unit will also have its own dynamics, isn't it? Then once we get this ym we are going to compare with the set point value. So ysp minus ym gives me the error and this error signal is given to the controller and controller based on this error signal is going to give you the actuating signal Cp, isn't it? And this actuating signal is given to what? This actuating signal is given to the final control element which is nothing but the wall or metering pump, isn't it? So you are giving an electric signal to a wall. There is a stepper motor on the stem of the wall. Depending on the electric signal, this stepper motor is going to rotate in a particular value of degree. And based on that, your flow rate of the steam or flow rate of your manipulated variable is going to vary. Okay, so this is the typical feedback system. Now feedback system is commonly used in process applications primarily because you don't have to identify the disturbance. Remember, you only have to see how much your system is messed up. And identifying the disturbance is not easy when you are having a complete plant. So that is the reason why feedback system is more popular in a process industry. Okay, so some examples are given here. The first one is a composition control. Here you can see that our aim is to maintain the concentration of product coming out at the distillate, isn't it? So what we are going to do? We are going to measure the composition of the distillate by using a composition analyzer, isn't it? And that composition we are going to compare with the set point value and difference of that is going to give me the error. And this error will be given to the controller and depending on the value of the error, the controller is going to manipulate the reflux ratio to the distillation part, isn't it? So this is composition control. Here you can see that the controller is denoted by Cc and composition analyzer is denoted by Cp. Okay. Similarly, in the second example in a pressure control, Here we are interested in maintaining the pressure inside the tank. So what we have to do? We have to first measure the pressure inside the tank by using differential pressure vane. This measured pressure is then compared with the set point value, and difference between set point pressure and the measured value of the pressure, that will give you error. Error is given to the composition controller, isn't it? And pressure controller, and pressure controller, depending on the value of error, it is going to open or close the wall, and because of that the pressure will be released or allowed to build up, isn't it? In a flow controller, we can measure the outlet flow rate here by using differential pressure set, compare with the set point value, that will give you error, and depending on the error, flow controller is going to manipulate the inlet flow rate. Okay. Last example is a temperature controller. So in this case you can see that we are interested in maintaining the temperature of the outlet stream, this particular stream, which is shown by a blue color here. Okay, so here you can see that the blue colored stream is a cold stream and the red color stream is a hot stream, isn't it? So this cold stream is exchanging, this hot stream is exchanging heat with the cold stream. So typically we wanted to increase the temperature of this cold stream, isn't it? Now in this case, what we are going to do, we are going to measure the temperature of this outlet stream here by using thermocouple, and then we can check whether this measured value of temperature is same as TST. If it is not, that will give me the error, and depending on the error, controller is going to manipulate the flow rate of hot stream, and by doing that we can maintain the temperature of the outlet cold stream. Now in these four examples you can see that the controllers are represented by CC, PC, FC and TC. And the corresponding measurements are represented by CT, PT, FT and T. So in this case typically the measurement is represented by CT. So here the first letter is for a particular variable. So C here for composition, P is for pressure, F is for flow rate, T is for temperature, and this capital T is for the measurement. For controller that becomes just C. So this convention we have also discussed earlier, you remember, okay? So typically if you look at the hardware, those are present in a process control. So hardware are nothing but what? There is a process. Then we are having measurement instruments like sensors, isn't it? Then we are having transmission lines, controllers and final control elements. So process can be tank, heat exchanger, reactor, distillation column, etc. Measurement instruments which we have studied so far is thermocouple. Even we have seen manometer, isn't it? Correct. So thermocouple, differential pressure sale, chromatograph, these are the measurement units, isn't it? Then transmission lines, this we have not seen so far. So transmission lines can be pneumatic or electric. Okay. Where to use electric transmission lines, where we should use the pneumatic transmission line, that we will discuss. Okay. Controllers, feedback controllers, there are three types of feedback controllers, P, PI and PID. Note that these P, PI and PID, these are feedback controllers. These are feedback controllers. When we talk about the feed forward control, there are different types of controllers. We will see that towards the end of this course. Okay. And final control element, this could be a control valve or metering pump. Okay. Now, transmission lines, pneumatic and electric. So until 90s, people used to have only pneumatic transmission lines. So what these pneumatic transmission lines are? There is a steam which is flowing through a line, and based on the change in the pressure, the signal is passed from one location to the another. That is what the pneumatic transmission line. Okay. Typically, these are used with differential pressure cell. Even diaphragm walls are used in the book there is a model equation derived for diaphragm wall. Okay, we have derived the expression for manometer, isn't it? Manometer we have derived. When there is a movement of the fluid, there is a inertia coming into the picture, and what we are expected to get in that case? What we are expected to get? Inherently second order. So in case of diaphragm wall also you are expected to get inherently second order. That entire derivation is there in your book. Okay, please look at. So pneumatic transmission lines, nowadays these are completely abolished, but still these are used in some specialized cases. Particularly if you are, I am not sure whether you have done your training in the facilities related to defense. Have you seen ordnance factories? So ordnance factories still keep using the pneumatic transmission lines. There is a reason for it, isn't it? So you will see that everywhere there is a fire explosive materials are there, and if you use the electric transmission line, there is a hazard of explosion. And that is the reason why the places like ordnance factories still use the pneumatic transmission line. Okay? Anyone done their training in ordnance factory? No? Why नहीं? देखा भी नहीं होगा. सुना है कभी? नहीं सुना है. So I have visited once the ordnance factory. There are different units like in fact I have visited the unit of even RDX unit I have seen there. Ordnance factory. These are the factories which actually manufacture the explosives for government of India. Okay, all these military equipments are manufactured. Even fuels, rocket fuels are manufactured. So, not sure whether you have heard these names. Nitrocellulose, have you heard? Nitrocellulose is explosive. So, nitrocellulose typically kept with almost 30% moisture in it. If you don't keep the 30% moisture in that, then it explodes. But when you remove the nitrocellulose moisture from the nitrocellulose, then it is referred as nitrocellulose powder. Anyway, it's really, some of these units are really interesting units. If you get a chance, please do your training in such units. You will learn a lot of things. Okay. You will get to know how things are going and how chemical engineering is used. आप लोगों में से कितने लोग केमिकल इंजीनियरिंग में इंटरेस्टेड है? दैट इज questionable. Anyway, so the point I wanted to make here is typically the places where the fire hazards are there, pneumatic lines are still used. Okay, and otherwise all these pneumatic lines are now abolished and these are replaced by electric lines. Why? Because speed of response is fast. Electric lines quickly get the signal, isn't it? Pneumatic lines, you have to maintain the pressure. There is a lot of maintenance cost associated, isn't it? So until 90s, people used to have the pneumatic valves, pneumatic transmission lines. Pneumatic means what? These are pressure driven. Exactly, these are pressure driven. So these are abolished after 90s with the evolution of the digital control. Okay, so now everything is digital. Most of the cases it is digital, except for the cases where the fire hazards are. Okay. So now these three last points which we are there, we are going to look at slightly more detail. Okay. So let's start with the controller. Controller anyway we have discussed. Proportional controller, proportional integral controller, proportional integral derivative controller we have discussed earlier. But we are going to derive the expression for this now. Okay. So if you look at this particular feedback control system, where is the controller? Controller is between measuring device and final control unit. So whatever the signal is coming from the measuring device is given to the controller, isn't it? Here at the controller it compares with the set point, and based on that we get the value of error. And depending on the value of error, the controller gives the electric signal to the final control unit. This could be electric signal or it could be pneumatic signal, depending on what type of controller you are using. Are you using a pneumatic controller or you are using a digital controller? Okay. Is it clear to everyone? So that is what is written. Between the measuring device and final control element, there is a controller. Okay. So typically in controller, the actuating signal is given based on the error. Now what is error? Error is nothing but the set point value minus set point value of the control variable minus its measured value. Isn't it? So error epsilon t is given as yst minus ymt. Isn't it? And based on this error, the controller is going to give you a actuating signal depending on what type of controller it is, whether it is a proportional controller, whether it is a proportional integral controller, or whether it is a proportional integral derivative controller. Isn't it? So there are three types, P, PI and PID. We will see these three in detail. So proportional controller, as the name suggests, the actuating signal coming out from the controller will be proportional to the error. Proportional to the error, isn't it? So that is what is written. Here CT is the actuating signal. CT is the actuating signal which is proportional to the error. So you can see that Kc into epsilon t plus Cs, where Cs is nothing but controller bias. Okay. So if there is no error, in that case the output coming out from the controller will be Cs. It's a controller bias. Okay. Again, Kc is nothing but proportional gain. Proportional gain, it's a user defined parameter. You have to state the value of Kc. Remember, all the parameters associated with the controller, the user has to decide. Okay, user has to specify. Now let's say if you are an engineer and you wanted to buy a controller, you went to market. How you are going to buy? क्या बोलोगे? Proportional controller दे दो. So controllers are sold with a characteristic which is called as proportional band. You have to specify the proportional band. If you tell the shopkeeper that I want to have a proportional controller with a proportional band of 100, 50, 200, then he will give. What is proportional band? Proportional band is defined as 100 divided by Kc. 100 divided by Kc. So it is nothing but it gives a range over which the error must change to drive the actuating signal of the controller over its full range. Okay. So in this case you can see that typically the proportional band is varying between 1 to 500, isn't it? And you have to specify the proportional band to the shopkeeper and he will give you a corresponding controller to you. Of course you are not going to do that, but just to understand. Now this is the equation. In this particular equation you can see that your actuating signal, the sensitivity of your actuating signal Ct depends on what value of Kc you are specifying. Higher is the value of Kc, more sensitive is your controller, isn't it? Higher is the value of Kc, even for a small error you will get a higher value of Kc. So your sensitivity increases when the Kc increases. That means what? Lower is the value of proportional band, your sensitivity is higher. Correct? Isn't it? This is the reason why Kc is referred sometimes as a strength of the controller. Okay. Kc is sometimes referred as a strength of the controller. Higher is the value of Kc, more sensitive is your controller. Now let's look at the mathematics here. I can take this Cs on the left hand side, so Ct minus Cs, I will get C dash T, which is nothing but actuating signal in a deviation form. Ct minus Cs is nothing but how much the Ct value is above or lower the controller bias. Then it is a value of the controller signal in a deviation form. Correct. So if I subtract this CS from here, that we get as C dash T, that is given as KC epsilon T. Correct. I can apply the Laplace transform. I can apply the Laplace transform on both the sides. What I will get? I will get this as C dash S, and that is equal to KC epsilon S. I can rearrange, so C dash S by epsilon S, that will be just KC. Now here C dash S by epsilon S, this particular term is referred as what? It is referred as a transfer function of the controller. So transfer function of the controller is given as KC, directly proportional controller. And I am telling this again and again because whenever the proportional controller we are going to use later, we are going to use this transfer function directly. We are going to use this transfer function directly. So whenever I am saying a proportional controller, its transfer function is given by KC. Its transfer function is given by KC. Now let's look at the another controller, proportional integral controller. This is also referred as proportional plus reset controller. Why it is called as plus reset controller, that we will again discuss. Okay. So typical expression given is Ct is given as Kc epsilon T. So this first term is a proportional term, isn't it? Plus Kc by tau I integral 0 to T epsilon T dt plus Ch. This second term is an integral term. This is the same expression which we have studied earlier. I am using here directly now. Okay. So this is the proportional part and this is the integral part. Here you can see that Kc is what? Kc is a proportional gain. Kc is a controller gain. Whereas tau I is nothing but what? Integral time constant. Integral time constant. Okay. So in this case also I can take this CS on the left hand side. I will get C dash T. C dash T will be given as Kc epsilon T plus Kc by tau I integral 0 to T epsilon T dt. Isn't it? I can apply the Laplace transform on both the sides. If I apply the Laplace transform, what I am going to get here? Kc epsilon S. What about this term? Kc by tau I S. Whenever we take the Laplace transform of integral, we get 1 by S term. Isn't it? So in this case, we are going to get Kc by tau I S into epsilon S. Isn't it? If we rearrange all the term and find out the transfer function, which is nothing but C dash S divided by epsilon S, that is given as Kc 1 plus 1 upon tau I S. So this is the expression for the transfer function of the proportional integral controller. So whenever we will be using proportional integral controller, we are going to use this transfer function directly, which is given as Kc 1 plus 1 upon tau I x bracket close. Correct? Now let's look at this equation little bit, in more detail, in a graphical way. So see, at time t equals to 0, what will happen? This error is 0. So this term is going to become 0. This particular term is going to become 0. So at time t equals to 0, Ct will be equal to Cs. Isn't it? So that's what we are getting here. See, up to time 0, we are getting the controller signal which is Cs. Exactly at time t equals to 0, the higher time than 0, you can see that this particular term will come into the picture. The time greater than 0, isn't it? But this another term will be more or less 0. So you will have only Kc epsilon t. So you will have this particular term Cs plus Kc epsilon. Cs plus Kc epsilon is what you are going to get. And as the time progresses, let's say the error is constant. As the time progresses, when time is equal to tau I, this entire term is going to become what? This entire term is going to become Kc epsilon. So you can see that this Kc epsilon and this Kc epsilon, that becomes 2 Kc epsilon. So that means your initial signal became double when time is equal to tau I. Your initial signal became double when time t is equal to tau I, and that is the reason why this entire controller is called as a reset controller? Because when your time is equal to tau I, your signal is getting reset. Okay, that is why it is called as proportional plus reset. So additional this Kc epsilon term you get when time is equal to tau I. So every tau I Kc epsilon term is getting added. Every tau I time your Kc epsilon term is getting added in the previous signal, isn't it? Correct? Alright. Now another interesting thing about this particular controller is you can see that this particular term integral term, this particular term keep on increasing, isn't it? And this particular term will keep on increasing as long as there is a non-zero value of epsilon. As long as there is a non-zero value of epsilon, as long as there is an error associated with the system, your controller output will keep on increasing. And that is the reason this particular controller has a potential of eliminating the offset completely. That is the reason why this controller eliminates the offset completely. Okay. But it also comes with a problem, isn't it? I might increase my controller might increase the electric signal, actuating signal, and that actuating signal is given to what? It is given to the wall. But wall can open up to 360 degrees. Even though my signal is let's say 400 degrees, can I open 400 degrees? It is not. So beyond a particular value of the controller signal, the physical limitations comes into the picture. Even though the electric signal is continuously increasing, but your wall is not going to increase beyond a time, beyond a value, isn't it? And that particular situation is called as integral binding. That is something called as integral binding. Okay. Let's go to the next controller, which is proportional integral derivative controller. So in this case, the additional derivative term comes into the picture. So this Kc tau d epsilon by dt, this particular term comes into the picture. So here what we are doing, my actuating signal is proportional to the rate of change of error. Rate of change of error, isn't it? d by dt is the rate of change of error. So as my error is continuously increasing, in that case my actuating signal will also increase. When my error is actually decreasing, even though it is above 0 but it is decreasing, then in that case it will add a negative value, isn't it? And why that is important? Because all these errors are calculated based on the measured value, and measured values are those values which are actually happened a time ago. It's not happening in that particular time. So you have to be conservative in applying the control action. So this particular term is actually anticipating whether the error is increasing or decreasing. And because of that, addition of the derivative control actually stabilizes your response. We will prove it mathematically later. So whenever you are having a derivative control, it actually stabilizes your control system. Okay, because it anticipates whether the error is increasing or decreasing. It anticipates the future value. And based on that, it is performing the corrective action. Okay. So now, in this case also, I can take this here from the left hand side, we will get c dash t. This is the equation I am going to get. I can apply the Laplace transform. So I will get Kc epsilon s here. In the second term, I will get Kc by tau I s epsilon s. And the last term, derivative control. The Laplace transform derivative is what? S into epsilon s in this case, isn't it? So if I take all the common terms out, what we will get is c dash s by epsilon s, that comes out to be Kc 1 plus 1 upon tau I s plus tau ds. So this is the transfer function of the PID controller, and we are going to use this equation whenever we use the PID controller. We will not derive this, we will directly use. So in this case, you can see that Kc is a controller gain, tau I is a integral time constant, and tau d is a derivative time constant. All these three parameters are user defined parameters. So you have to specify the value of Kc, you have to specify the value of tau I and tau d. Okay. Now there is an advantage with this control system and there is a disadvantage. The advantage is this rate of change of error actually anticipates whether the error is going to increase or decrease, and because of that it is going to add the stability to the control system. That is the advantage. Disadvantage is let's say I am having an error something like this. Maybe I'll do it. Let's say I am having an error which is epsilon t, let's say I am plotting. Epsilon t is decreasing with time, decreasing, and then it becomes constant. It's constant. So this is the value equals to 0. This is the 0 value. So I am having the error which is decreasing initially, and then it became constant. When the error became constant, what will be the contribution of this derivative term?
0.
It will be 0. Even though I am having a non-zero error, remember this much error is still present in the system. I am having a non-zero error, still the contribution of the derivative control is 0. Contribution of the derivative control is 0. Another case here is, let's say I am having the error. Let's say this is the 0 line. So my error is something like this. These are the error value. On an average, my error value is 0. Remember here, error value is based on how much y you have measured, and ym is being a measured value. You can have measurement errors there, isn't it? You can have, your measurement may not be accurate. You might be having some fluctuations in your measurement. So even though the error is on an average 0, but still your derivative control will have some value. Why? Because it will look at this particular error like this. It will look like this, isn't it? Even though the average error is 0, but your derivative control is going to give you some control action, isn't it? When the no control action is actually required. So whenever you are having a noisy error data, application of the derivative control is going to give you wrong value. Is it clear to everyone? So these are the two disadvantages of the derivative control. Now we have already seen the measuring devices. So measuring devices like venturimeter and orifimeter, that will be what? The flow rate is proportional to the under root of pressure drop, isn't it? So wherever there is a flow of the material is taking place, in that case we are expected to get a second order differential equation like this. So you are expected to get a second order transfer function, isn't it? So this particular equation is for pressure actuated signal. One of these we have already derived. Remember, manometer we have derived. We have derived the expression for manometer. In that case, the same equation we have obtained. Okay. So all the pressure actuated measuring devices will be denoted by a second order transfer function. Kp divided by tau square s square 2 zeta tau s plus 1. That is what we are going to use for all pressure actuated equipment. Then, if you are having, let's say, temperature sensor, thermocouple. Thermocouple is usually a first order process when we are looking at only the resistance present in the outer layer. Remember, the layer which is present outside, air layer which is there, the liquid layer which is there, outside the thermocouple, we are only assuming the resistance there. But let's say if we assume the resistance inside, let's say outside layer is there, but similar to that, let's say there is a layer inside the mercury bomb. If you are assuming the resistance there, in that case you are going to get a second order transfer function like this. In fact, this is one of the unsolved questions in your book. This is one of the unsolved questions given in the questionnaire in the book. Okay. Then transmission lines. Typically the dynamics of the transmission lines we ignore. we ignore the dynamics of the transmission lines unless the system response is very fast compared to the transmitter, or the transmission lines are very long. Let's say pneumatic transmission lines you are using and these are very long. In that case, you have to use the dynamics for the transmission lines as first order process with date time. So first order process with date time is given by this e raised to the power minus CDS divided by over S plus 1. Here this CD is the date time. Again here P0S is the outlet pressure, whereas PIS is nothing but the inlet pressure of the pneumatic pressure lines. Okay, is it clear? So typically the dynamics of the transmission lines we ignore. Only in the case where the system response is fast or the transmission lines are pneumatic and these are located over a long distance, in that case we use the first order dynamics with date time. Otherwise we ignore. Okay. Now the last part in this particular chapter is whether we are having a tutorial this Friday. We are not having a tutorial. This Friday is no class day. Okay, so I will just quickly go through this and then we will stop. So this particular experiment is there in your lab next semester. Wall characteristics is one of the experiments which you have to do in the next semester. Okay. So there are two types of walls. This particular wall, these are the two pneumatic walls. You can see that depending on the air pressure, your wall is actually open or closed. In this case, this particular wall is a fail open. So whenever this input fails, what will happen to this plug? This plug will open, it will go up. So you will have a fail open. Similarly, the second wall, when this air input fails, what will happen to this particular plug? It will go up and the wall will close. So this is a fail close. So depending on the structure of this plug, the characteristics of the wall changes. Okay. In fact, three different types of walls you have to study next semester in process control. Okay. The same thing is given here. You can see depending on the plug shape. If you are having a plug like this, then you get f of x equals to under root x. Here x is nothing but the same position. Remember the same is there, which comes up or goes down. Depending on that, the flow rate increases or decreases. So same position is given by this f of x. So you can see that the outlet flow rate is given as k f of x under root delta p by rho. Here this f of x is coming from the characteristic curve, and these are the characteristic curves which depend on the shape of the curve. Anyway, we will cover this in the next class. Okay. So we will stop here unless you have any question. Please note that the quiz will be on 28th October. So there is a gap in between. I think mid-sem break is there. Please utilize that mid-sem break wisely, isn't it? Because the questions are going to be, those will be going somewhere here. So please go through all these solved, unsolved examples. If you have any doubt, anything you wanted to ask me, feel free to come. Feel free to ask me after the tutorial. Okay? Minor copies I wanted to show you today, but some copies are left. So tomorrow you all will get to see your minor copies. So please ask your friends to come tomorrow. I am not going to show later. Okay? Only tomorrow we are going to show you your copies. This syllabus will be whatever we will cover till that point. There is one student who did not submit the assignment given. Okay, क्या नाम है भाई? हाँ, 6 में से 6 लोग हैं ना, जिनसे प्रॉपर्टी लिखा था. So there is one person who did not submit. You are likely to get 0.
20.
पेपर करके फिर से कंफर्म कर लें.
Everyone.